In this video, we'll be solving IGCSE Chemistry 0620 paper of Summer 23 series question paper 62. We'll also keep on discussing some important tips of solving paper 6. So let's not waste the time and start with question 1. Here is question 1, which says hot powdered lead oxide is reduced by methane, a flammable gas. So here what are we doing? We are taking an lead oxide in the powdered form and reducing it with the help of methane, which is a flammable gas. The products are lead, steam and carbon dioxide gas, and here shows the apparatus to reduce the lead oxide. So here is the methane gas being passed in a tube, and here is the powdered lead oxide shown in this area in the tube, and then there is a tube which is passing towards the test tube, and here we can see in the beaker there is an ice. So now the sub question 1 says, A says that name the item of the apparatus labeled A. Now A is labeled here, which is filled up with the ice, so we can label that as in beakers because that's the beaker filled of ice. Draw an arrow on figure 1.1 to show where the apparatus should be heated. So it's the apparatus where it should be heated on the powdered lead oxide. So here we are drawing an arrow on the lead oxide, so an arrow pointing upward towards the lead oxide. That's important, where the lead oxide is heated. Okay, let's go ahead with the next sub question, where it says the part C says explain why powdered lead oxide is used and not a large lump of lead oxide. Now the simple theory behind this is that if we use large lumps, the surface area decreases. So we use powdered lead oxide because powdered lead oxide have high surface area, which increases the rate of a reaction. That's the simple logic, that why do we have the high surface area, which increases the rate of reaction, so that we can understand that the lead oxide will be reduced faster if we increase the surface area. Okay, let's go ahead with the next sub question D, where it says explain what happens at the point labeled B on figure 1.1. So let's go ahead and see where is point B in figure 1.1. Okay, figure B here, it's in figure 1.1. the B is here, which is in the test tube and where the tube is pointing down. Now if something is passing in the tube, let's understand what is being passed. So what is being passed is the products are lead, steam and carbon dioxide. Now if lead is solid, it's not going to pass from the tube here to the another tube. So what is going to pass are the gases formed as a product will pass. So the steam and carbon dioxide gas passes off. Now if the steam is passing off and here is the ice to cool down, the steam is going to condense back into water. So what is going to happen at the point labeled B? So we can write that the steam condenses into water. And if it's 2 mark, let's try to elaborate it to make it a 2 marks, that so colorless liquid will be seen. So colorless liquid will be seen. Why? Because now steam has changed to water, so colorless liquid is seen and the steam condenses to water. Now the waste gases contains methane. State why the waste gases should not be released into the laboratory. Simple reason that the waste gas is methane, and in the question it is written methane is flammable gas. So let's write here that methane is a flammable gas. As simple as that, methane is a flammable gas. That's what we need to explain. We don't need to elaborate more than this because it's just an 1 mark question. So here if we go to the next sub question, okay, this question is over and we are having a question 2 here. Question 2 says a student investigates how the rate of reaction between aqueous iron 3 nitrate and aqueous sodium thiosulfate changes with the temperature. So what are we changing here is temperature, and we are finding out how does changing the temperature affects the rate of the reaction. And the student does 5 experiments using the apparatus shown here. Now what's the apparatus shown here is a beaker which contains 50 centimeter cube of aqueous iron 3 nitrate. It's an 100 centimeter cube beaker, and there is a printed sheet with some printed text on it. And let's go ahead and read experiment 1. But what I suggest is that reading the whole procedure is going to take a lot of time, so you can pause the video and read the whole experiment. By the time I can go ahead and explain you the next sub questions. So let's just go ahead with sub question A. Okay, here are the table 2.1 where different clock are shown, and we are, I think, supposed to fill up the whole table. Let's go ahead and see if there is any sub question. Use the thermometer diagrams and stop clock diagrams to complete table 2.1. So here are we supposed to complete the table. Here we can see that becomes visible, that is, and we have to write seconds, the time in seconds. So what is this time in seconds meant for? It's meant for time taken for the text to become visible. So here is the time we are supposed to write in the seconds only. So if we go ahead with the time, then the first clock we can see that there is 1 minute already gone, and after 1 minute there are so many seconds. So if we calculate, there are 50 more seconds after 60 seconds, and then one more. So total is going to be 116 seconds. If we go ahead with the next clock, it's only 1 minute passed, and then there are almost 20 seconds gone ahead. So the total will be 80. 60 plus 20, it's going to be 80 seconds. Next is 1 minute passed. You can see that there are 9 seconds past 1 minute. So 69 seconds. 60 plus 9 seconds. Next is only 1 second ahead of 45, so it is 46 seconds. And the last clock here is only 20 and 21. Yes, so it's 21 seconds. So all the seconds are done. Let's go ahead with the thermometer diagram where the temperature of the solution when text becomes visible, that is in degree Celsius. So if we look at the temperature here, it's 25, so 24, 23, 22, 21, but the reading is not fully reaching 21. So what we can write is 20.5 degrees Celsius. We can see that the thermometer level, mercury level, is not exactly reaching 21. So in between we have to write 20.5. We go ahead with the next, it's 22 marks more than 25, so it should be 27. 27.0 I would write, because here if we are writing in 1 decimal place, the other readings also has to be in 1 decimal place. Here the next reading is exactly 30, so 30.0 I'll write. The last, you can see that it is 37, so 37.0 degrees Celsius. And one more thermometer reading is left, and that is again 45, 46 and 47, in between 46 and 47. So the reading should be 46.5 degrees Celsius. Okay. Write a suitable scale on the y-axis and plot your results from the experiment 1 to experiment 5 on figure 2.2. Draw a smooth curve of best fit. So I'm drawing the curve. I'll again pause the video. I'll draw the curve and I'll show you. So here you can see I've completed the graph, and on y-axis you can see that I've taken time in seconds. I've chosen a suitable scale where our the temperature time was ranging from 20 to 116. So I've chosen a scale where here you can see that I've chosen 5 units as 10 seconds, and so it covers all of our seconds till 116. And on x-axis they've already given the temperature, and here I have plotted the points. As you can see, there are crosses in blue, and I've tried to draw a curve in red so that it is visible properly. Actually, the curve which I've shown here is not a smooth curve. As I'm drawing it digitally, it has gone little here and there, but definitely with a pencil you can draw a very smooth curve. So let's go ahead with the next question, where okay, it says that deduce the experiment in which the rate of reaction is fastest. Now, if we are talking about rate of reaction, the seconds it will take least is going to be the fastest reaction. So let's see which is taking the least time. So here we can see that there were 5 experiments conducted, and the least time taken was the last experiment, that is the 5th experiment with the highest temperature. Took the least time. So what we can write is deduce the experiment they have asked. So we can say that the 5th experiment is having the highest rate because it took the least time. Now it says that use your graph to predict the temperature of the solution when the text becomes visible after 55 seconds. Show you're working on figure 2.2. So remember, here we are supposed to work for 55 seconds. So as time on y-axis, we can see that 55 seconds are somewhere here, and so let's go ahead and draw the lines. So now here I have drawn the lines from 55 seconds, you can see, and if we work out the temperature, it's 31, 32, 33 and 34 degrees Celsius. So if we write the answer, it's 34.0 degrees Celsius. I always prefer writing in 1 decimal place because the thermometer reading reads up to 1 decimal. So we need to write up to 1 decimal for each and every answers wherever it is possible. So let's go ahead with the next sub question. It says explain why wrapping the beaker in cotton wool after it has been heated will improve the accuracy of the results obtained. Now, to answer this question, let's understand what is actually happening. What are we doing is we are changing the temperature of a reaction mixture. We are changing temperature of the reaction mixture and finding out the time in seconds to complete the reaction. So here if we are measuring the temperature, then wrapping the cotton wool will have to do something with the insulation. So here we can write that the cotton wool is now read the question again. What it is written: explain why wrapping the beaker in cotton wool after it has been heated will improve the accuracy of the results obtained. So here we are wrapping the cotton wool after heating, so that shows that it will have a good insulation. So we can write that cotton wool will provide insulation, and so it will prevent heat loss. So if heat loss is prevented, that shows that the temperature will try to remain constant, and that's why the accuracy will be obtained. So it will prevent heat loss and temperature remains constant. So if temperature remains constant, our results will be more accurate. Let's go ahead with the next questions. Here the sub question F. It says explain why it would be an improvement to measure the volume of aqueous iron 2 sulfate in a burette rather than a measuring cylinder. Now simple logic here is burette is more accurate. Burette gives more accurate readings. That is the only reason, because burette and pipette are the apparatus which measure the volume to more accuracy. Okay, suggest why. Next sub question: suggest why it would not be an improvement to add aqueous sodium thiosulfate using a pipette. Now let's understand the question again. What are we doing is we had taken iron nitrate, iron 3 nitrate in the beaker already, and then we are adding sodium thiosulfate, and the moment we add the sodium thiosulfate we are starting the stopwatch, so that because the reaction starts immediately the moment we start adding sodium thiosulfate. Now if we use pipette, the problem is that the adding of sodium thiosulfate solution through pipette is going to be very slow, and the moment we start adding dropwise, the drops falls, the reaction starts. Now this is going to be a problem because all of the sodium thiosulfate won't be added all of a sudden, but the reaction starts. So here we can say that it would be very slow, it would be very slow and decreases the accuracy, because here to get a better result we need to add whole of the thiosulfate immediately. So here it would be very slow, it decreases the accuracy. So here I need to improve my spelling, accuracy. Okay, so suggest why the aqueous sodium thiosulfate must be added after aqueous iron 3 sulfate has been heated and not before it is heated. Okay, now again if we understand the whole experiment, it's again as we have already discussed in F2, the moment we add the sodium thiosulfate the reaction would start, but if we heat after it the temperature will be increasing during the experiment, and so we won't get our answer exactly at a particular temperature. So we can't measure the temperature accurately, that when did the reaction occur at what temperature again. So what we need to write here is that the temperature increases during the reaction or while the reaction is happening, during the reaction, which will again decrease the accuracy, decrease the accuracy. We need a constant temperature when the experiment is happening. That is what is needed for the accuracy. So here the temperature should remain constant and should not change. So that's why we need to heat the experimental solutions before the reaction starts. Let's go ahead with the next question. Here the last sub question says, describe how the results of the experiment would change when the experiment is repeated using 250 centimeter cube beaker in place of 100 centimeter cube beaker, and explain your answer. Okay, again to understand this question, let's go ahead back and read few more lines of the question where we can understand what exactly is happening. Now here we can see that it's written in the next step here that look down from above the beaker. When the text on the printed sheet becomes visible, stop the stop clock. So now what we are doing is we are looking from the top of the beaker and we are trying to see when the text becomes visible, and when the text becomes visible we can make we stop the stop clock and measure the time. So if the beaker is shallow, in fact the beaker is bigger, if the beaker is bigger, then the solution used inside it will be shallow. It won't take a big depth. So what is going to happen is the solution is going to become transparent very easily. Because the depth is less, we'll be able to see that the transparency of the solution becomes faster. So what changes in the result is time will be shorter. The reason being is that explain. So explanation you have to give the reason. The reason being is that the depth of the reaction mixture decreases. And so the change is visible, the change is visible easily, and that's why the shorter time will be taken to observe the reaction change, and so the time also will be shorter, the time noted will also be shorter. Now let's start with question 3 here. Question 3 states that a student tests two substances solution F in solid G. Test on solution F are shown here. So table 3.1 shows the test and the student's observation for solution F, and the student divides solution F into 3 portions. Now you should remember that F is a solution and the tests are given, and from the test we need to identify the solution F. So what are the you can say cations and anions present in solution F that we need to identify from this table. So the first test which is given is do a flame test on the first portion of solution F, and light green color is obtained. On the second test, it's written to the second portion of solution F, add a 1 cm depth of aqueous sodium hydroxide and a piece of aluminium foil, warm the mixture gently and test any gas produced. Effervescence seen and the gas turned damp red litmus paper blue. So here if the damp red litmus paper is turning blue, then the gas produced is ammonia, but then this ammonia is produced only by heating the solution F with NaOH and aluminium foil. Remember the test, because we'll be checking this test at the last page of the question paper 6, where the tables for the cation, anion and the flame test, everything is given. So let's go ahead with test 3 also. To the third portion solution F, add 1 cm depth of dilute nitric acid followed by a few drops of silver nitrate, and no change is given. Now if we check the table, we'll understand that the silver nitrate test is for the halogens, halide ions. Halide ions are chloride, bromide and iodide, but as there is no change, means these anions are not present, that is halide ions are not present. So if we identify, we need to remember the two tests. First is the flame test color of light green, and the second test is for anion, where we are heating it with sodium hydroxide and aluminium foil. So let's go ahead and check with our cation and anion test table, which is given at the end of this paper. Here it is. Now if we look at the test, where we can see here that in the nitrate test, the aqueous sodium hydroxide and aluminium foil warm carefully, that is the test given in the ammonia test. Ammonia gas is produced, so that shows that this gave us a positive test of nitrate ions. So in our solution F, nitrate is present. Now let's go ahead with the flame test also. Let's check for the flame test, where we are getting an light green color test. If the flame test is light green color, that shows the barium as an cation is present in our solution. So we have already identified that barium as an cation and nitrous as an anion is present in our solution F. Now let's go ahead and look at the questions of describe how do the flame test used in test 1. How do the flame test used in test 1? So we are supposed to explain that how is the flame test done on the solution F. So we can say that the substance or the solution or the solid should be taken on the wire. We can say that here, if a solution, we can dip the wire into the solution. So we can say that dip a wire in the solution F, in the solution, and put it in the blue flame of the Bunsen burner. Blue flame of the Bunsen burner. Now we need to specify that we need to use the blue flame of the Bunsen burner, because that's the flame where there is an highest temperature and that gives us the proper color. So we need to specify that we are keeping the solution or the solid on the wire and keeping it in the blue flame and then observing the color. So here if it's 2 marks, we also need to mention that observe the color. So dip the wire in the solution and put it in the blue flame of the Bunsen burner and observe the flame color. Observe the flame color. That's we need to specify, because it's a 2 mark. Describe the whole process where how is the flip test performed. Let's go ahead with the question B, where it says identify the gas given off in test 2. We have already seen that if the red litmus paper turns blue, the gas is ammonia. So we are writing ammonia gas is produced in test 2. So identify solution F. Now we have already identified that the solution F is barium, so we can write Ba2 plus and NO3 minus, or we can also write it in the name that it's barium nitrate. We can also write it in the same way. So we can specify the 2 ions in the formula, that is Ba2 plus and NO3 minus, or we can write the whole name of the solution F as our choice, doesn't make any difference. Okay, the D sub question state what would be observed if the student adds dilute sulfuric acid to another position of solution F. Now let's understand this test. If we go ahead and check a test table below, then we would find that the sulfate test has an acidified dilute nitric acid, or you can say an acidified barium nitrate is used to test sulfate ion. Now yes, barium nitrate is present in our solution F and we are adding sulfuric acid. Now sulfuric acid obviously contains sulfate ion, that is H2SO4, and this sulfate SO4 minus and barium nitrate together gives white precipitate. So if we are mixing sulfuric acid or adding sulfuric acid to barium nitrate, obviously the observation will be white precipitates, which is actually the test of sulfate ion, but here we are doing the reverse process, that we are adding sulfuric acid to the barium nitrate. Okay, so white precipitate will be observed. Now let's understand the test on solid G. The test on solid G. Solid G is iron to carbonate. So here we need already know that the cation is Fe2 plus and the anion is CO3 2 minus. Now before we go ahead, let's go ahead and check the test of Fe2 plus and the carbonate ion. Now carbonate ion, here we can see that in the test of anion, add any dilute acid. Any dilute acid is added to carbonate. The test of carbon dioxide gas will be seen, that is the effervescence will be seen, and the gas produced during the effervescence, that is carbon dioxide test. So it will turn lime water milky, because the test of carbon dioxide is turning lime water milky. So this should be the test given for the carbonate ion, and let's see what is the test of Fe2 plus. Fe2 plus, now we can say that here it is, and when aqueous sodium hydroxide as mentioned here is added to the solution containing Fe2 plus, will get green precipitates which is insoluble in excess and turns brown near the surface on standing. So remember, it gives green precipitates which is insoluble in excess of sodium hydroxide solution. And if we add aqueous ammonia to the Fe2 plus, again we get green precipitate which is insoluble again in the excess of ammonia solution, again turns brown near the surface on standing. So the test for the Fe2 plus is same for adding both aqueous sodium hydroxide and aqueous ammonia. So let's go ahead and check here that what is the test on G. The sub question E says about 10 centimeter cube of dilute sulfuric acid is added to solid G and any gas given off is tested. So here the observation as I said, if we add any dilute acid to the carbonate ion, effervescence are seen. So we can write effervescence are seen, effervescence are seen, effervescence are observed, effervescence observed, and the gas produced turns lime water milky. Or you can also write lime water turns cloudy. That is also acceptable here. You can always again check the test given on the last page about the carbon dioxide gas test and the carbonate once again before you put the test in the words. Okay, let's go ahead with the sub question F. It says to the product from E, aqueous sodium hydroxide is added dropwise until it is in excess. Now the products here to the solution F. Now what has happened? We have iron carbonate, iron 2 carbonate, and if we are adding sulfuric acid to it, obviously the carbon dioxide has evolved off. The product will be ferrous sulfate, Fe2SO4. That is, sorry, Fe2SO4, sorry, FeSO4 is produced as a product. Now to that FeSO4, that is ferrous sulfate, iron 2 sulfate, if we are adding sodium hydroxide, again that is a test of Fe2 plus as we have already seen in the table earlier. So if we are adding it dropwise, we'll get green precipitates as we had already seen in the table, cation table. Observations in excess. Now on adding excess, we had also seen that it remains insoluble in the excess, insoluble precipitates. So we can leave writing this, green precipitates remains insoluble. So here our question 3 ends. Let's go ahead with question 4. If we have any doubts here, we can always go back to the table and check once again before writing anything. So here I think this question 3 is quite easy. So let's go ahead with question 4. Question 4 says a metal polish is a mixture of 4 substances. The properties of these substances are shown in table 4.1. So a metal polish contains a propanol, ethanoic acid, iron 3 oxide and silicon oxide, and their solubility in water is given. The 2 of the substances are soluble and the remaining 2 substances are insoluble. The reaction with dilute nitric acid, the both dissolves. The first 2 substances, that is organic substances propanol, ethanoic acid, dissolves in water also and reacts with the dilute nitric acid also. If we talk about iron 3 oxide, it reacts when warmed to form a soluble salt. So iron 3 oxide reacts only when it is warmed, and silicon 4 oxide does not react. So silicon 4 oxide, you can see that it doesn't dissolve in the water also and doesn't react with the dilute nitric acid also. Now let's read the main question. Here it says plan an experiment to find the percentage of biomass of silicon 4 oxide in the mixture. Your plan should include how you will calculate the percentage of silicon 4 oxide in the mixture. You are provided with a sample of metal polish, dilute nitric acid and common laboratory apparatus. Now let's understand the question. What are we supposed to find is percentage by mass of silicon 4 oxide. Now if percentage by mass of silicon 4 oxide we are finding, we need to separate silicon 4 oxide from the mixture. Now as we have already seen, silicon 4 oxide is insoluble in water as well as with dilute nitric acid. It doesn't show any reaction, so we can easily separate it. But remember, iron 3 oxide reacts with dilute nitric acid only when it is warmed. So here if we plan out something, we need to find out that what are we going to keep same, what are the apparatus we are using. So what are the apparatus we are using, that we need to remember. We should mention it if possible mention the quantity or the measurement of the apparatus also, but that is optional if it is required, otherwise we may not mention also. Okay, here, so if we start, we can start with take a known sample, take a known mass, I would say take a known mass of metal polish in a beaker. Now why am I using a beaker? Because we need to mix the water and nitric acid in the beaker, and the best apparatus to mix certain mixtures, the reactants, is a beaker. So take a known mass of metal polish in a beaker. So we know the mass of the metal polish. Now knowing the mass is very important because we are going to find the percentage by mass of silicon 4 oxide. So the known mass of metal polish is required. If we want, you can mention also that we can take 2 gram or 5 gram of the metal polish. In place, I've just written here known mass. Means before using, we are calculating, we are measuring the mass. That is important. Okay, next what we are doing is add excess dilute nitric acid. Why am I specifying excess? Because all of the possible substances should dissolve and react in the dilute nitric acid. Now if we are already using dilute nitric acid, that means it contains enough water also. So the substances soluble in water will dissolve, and the substances which are going to react with the nitric acid, that is also going to react. Now as we know that iron 3 oxide reacts only when it is warmed. So what we can add here is warm the mixture so that even the iron 3 oxide dissolve. So warm the mixture and stir it so that everything dissolves properly. Now the next thing is that all the 3 substances remaining, propanol, ethanoic acid and iron 2 oxide, would have dissolved and reacted with nitric acid by now. Silicon 4 oxide is not going to react, so it's not going to dissolve, and so we can remove it by filtration. So the next step is filter the mixture. And then what we are going to do is collect it from the filter paper. So but I'll say that here, wash the residue, that is whatever is left in the filter paper, that is residue. Whatever is left, the solid left in the filter paper is residue. So wash the residue with distilled water. Now this is not compulsory, but still I always prefer that specify wash it with distilled water. So that all the impurities are also removed. Dry the residue between the filter paper, so that the water is also removed. Now as silicon 4 oxide is dry, then we can measure the mass of the residue. So measure the mass of residue. Now we know that the residue is silicon 4 oxide. Now if we know the mass of the silicon 4 oxide, the percentage of silicon 4 oxide, that is SiO2, we can say that mass of residue divided by the mass of metal polish, because that was the total mass of all the 4 substances present in the metal polish. On the top is mass of residue, that's the only mass of silicon 4 oxide, and multiply by 100. That's going to give us the percentage of silicon oxide by mass. So this is how we are going to calculate the percentage by mass of silicon 4 oxide present in metal polish. So now understand what have we done. We had taken a known mass of metal polish, reacted all the remaining 3 substances with the help of dilute nitric acid, and we obtained the silicon 4 oxide unreacted by filtration. We have measured the mass of the residue, and then we are calculating the percentage by mass of silicon 4 oxide in the metal polish with the help of this formula. And you can see that here that carries 6 marks. So it's important that you specify all the steps properly so as to get the full marks. So I hope this paper, question paper 6.2, is going to be very easy if you think from this point of view how to mention all the points as we have specified from the exam point of view throughout our video. What are the things we should keep in mind while writing, especially this last question where we are planning an experiment. What are the things we should specify? We should specify the name of the apparatus. If required, specify the capacity or the volume of the apparatus. If the formula is needed, write the formula also, because that's also going to give you marks. Formula is needed as it's also written in the question. You can see here it's written in the question that include how will you calculate the percentage of silicon 4 oxide in the mixture. So how are you going to calculate? With the help of the formula. So specify the formula also. That is also very important.